So today's second speaker, Kazim Buyukboduk, University College Dublin, and he will present word crossing, GGP, and periodic Artin formalism.
Thank you very much for the introduction, and well, thank you, I guess, to ICTS for hosting us in this great facility, and thank you, the organizers, for the invitation and giving me the chance to speak. It's great to be among colleagues and friends here. So, I mean, this is joined with a bunch of people, which the names will come up, and I apologize for not stating this now. So I'll start with the motivation and the background, which basically boils down to the BDP formula, where we fix a prime, an odd prime, and also embeddings of embedding of Q bar into CP is fixed, as well as an isomorphism between complex numbers and CP. Everything that I have to say will depend on those choices. So F is a cuspidal eigenform of weight at least 2, weight K at least 2, and P is a good ordinary prime for F, and K is an imaginary quadratic field satisfying the Heegner hypothesis relative to N, which is the level of this form. I don't know if this is working, but it's okay. All right. G is CM Hida family by K. Okay, that we fix. And F is the unique Hida family through my cuspidal eigenform F, or it's the ordinary P stabilization. And what we're interested in is basically the central critical values of these Rankin-Selberg L series. So basically we have these Rankin-Selberg L functions of specializations of the family F and G at kappa and lambda. And we're interested in the central critical L value. So C is weight of kappa, weight of lambda minus 1 by 2. So this is the central point. So basically the first, okay, to study these numbers, I guess the first first player is the root number. So how does the root numbers behave? So it depends on basically how the weights of F and G are ordered. So basically in the so-called F-dominant range, which is basically depicted here in this picture. So I'm basically here sketching weight of F against weight of G. Okay, so whenever the weight of the specialization of this family F is larger than that of the G, then the global root number in this region turns out to be -1, which means for all these classical specializations of my Hida families, the L values are identically 0 at the central critical point, and somehow the arithmetic is governed by the Gross-Zagier-Zhang formula, which basically tells us that the central critical, the first order derivative of the L function is somehow given in terms of the Néron-Tate height of a suitable Heegner point. And of course, I mean, here I need to insist that the weight of kappa is 2 and weight of lambda is 1. So this is kind of a very restrictive case of what Gross-Zagier formula could say in this particular case. This will suffice for whatever I have to say later on, but so this is basically how it is. And also there's something funny here that I write this as a specialization of a big Heegner cycle as to points kappa lambda. So there's also a reason for that too that's going to come up in a second. But this is sort of what the picture looks like in the F-dominant range, where the sign is -1, we have a Gross-Zagier formula. Now, in the G-dominant range, we have the sign change then, okay? So when the weight of, so if you look at the range where the weights of G is larger than weight F, it turns out that the global root number is +1. And then now the arithmetic is governed by GGP in this case. I guess this is the Walsh-Bourget formula of Bertone, Darmon, Prasanna. So here you can express basically the central critical L value at those specializations where the weight of G greater than weight of F as some toric periods. And somehow these also behave well as you vary kappa and lambda periodically, so they interpolate well, and they give rise to this variational property gives rise to the periodic L function, the so-called BDP periodic L function attached to these two families. So these interpolate these central critical Rankin-Selberg L values as kappa lambda vary in the G-dominant range. So we have a periodic L function interpolating L values so long as we are on this range in this red domain. But then again, this picture is somewhat misleading because when you look at it, you don't get the impression that this range of classical points which live here are dense in the full weight space, but they are. Which means that like, if you take a point outside this range of interpolation, this range, for example, if you take a F dominant point, you can still restrict it to here and ask if this has any arithmetic meaning. So although the BDP periodical function has no direct connection to the values, to the points in the in this two-dimensional weight space, where the weight of the first vector is larger, it doesn't have direct connection to the L values there, still you might ask if this has any arithmetic meaning. So this is what I refer to as the wall crossing. You're basically moving from this range to the range where weight of F is greater than weight of G. And like, the answer to this is like the famous theorem of Bertrand-Darmon-Prasanna that expresses somehow this BDP periodical function. I guess this is like enhancement due to Castella. The BDP periodical function can be recovered from the Bicegner cycle as its logarithm. And somehow the slogan here is that, well, which I like to think about, like think of this as the periodic Gauss-Bourget limit formula, that if you basically take a specialization kappa lambda where the weight of the first vector is larger, so BDP periodical function doesn't admit this as one of the interpolating points. So if you basically look at the value of the BDP periodical function at this point, which you can think of this as like this limit of these toric periods over the range where you can really interpolate. So this is a periodic avatar for the central critical. This is a periodic avatar of the derivatives of the L series at the central critical point. Just because saying their points know exactly derivatives. I'll make this even more precise in a second. Okay. Sorry, someone was taking a picture of me, but I'll go on. So basically, I'd like to now describe the story concerning the triple products. It really parallels this, and as an application, I'll discuss the periodic Artin formalism that was in the titles. So we start with now two forms rather than three. I'll tell you what the third form in a second is. So F is a form on form with level P and F and character chi F of weight K. G is a form of weight L. So these are Caspida eigenforms. They are new away from P and they're old at P. Okay. So looking at P stabilized forms. And F underlined and G underlined, like as in the previous slides, they are just Hida families through F and G. And you see, I'm talking about triple products, and the third family, normally you can choose it independently, and much of what I'm going to say indeed will hold. But for the main purposes, like related to periodic Artin formalism, we're going to work with H, like we're going to choose H to be the conjugate family to G. So the conjugate family to G is simply given by twisting this G by, I guess I should have said primitive, like, maybe it is also automatic already. Yeah, this arises as the twist of the Hida family by the inverse of the central, the Taim-Leben type of the family G. So this is the setup. I start with three families, F, G, and G conjugate, basically, okay? You can just imagine that like the triple product will factor, and I'm gonna basically ask questions about that, okay? That's the main point. And just to set up a few further notation, RF underlined and RG underlined are the corresponding branches of Hida's universal algebra, okay? So these parameterize these families. And we're gonna work under the self-duality condition, okay? So a priori, it would read that, like, the central characters of F, G, and H should multiply to 1, okay? But since we're working with this family where G conjugate is the dual family, the central character of G and G conjugate cancel each other out already. So this amounts to that. The central character, this basically has no central character. And as a result, under this assumption, it turns out that, like, for all classical specializations, the local root numbers for these triple products are always plus or minus 1, okay? So when V is a non-Archimedean prime, it turns out that actually this value, the root number, the local root number at V of this specialization is independent of the choice of kappa lambda mu, so it only depends on the family. So at those primes, we're working with Hida, like this is somehow like in contrast with the previous talk, okay? So there was something funny going on at P. Here we don't have that issue because we're working with an ordinary family. So whereas the root number at the Archimedean place depends on how the weights are interlaced, okay? So that's basically, the root number will vary, as in the previous case, depending on how the weights of kappa lambda mu are arranged. Now, the first basic case, so there are going to be 4 ranges, like, there are basically 4 triangles here. The first case that I'm going to consider is the so-called balance range. So I'm going to denote this by this triangle based on this. So that basically means that, yeah, I mean, I realized just moments before my talk that it's a bad idea because also it suggests diagonal. It has nothing to do with diagonal, okay? Because that will also show up, unfortunately, as part of the talk. It has, I mean, multiple times, in fact. But yeah, this means like just simply you're satisfying the triangle inequality. So what this means is that, like, weight of F, weight of H, and weight of G verify all the possible triangle inequalities, okay? So basically, I'm assuming, so as I said, like, the local, so for all non-Archimedean places, the local root number is plus or minus 1. I'm going to work under the assumption that it's plus 1, okay? You can probably say, I mean, this is work in progress by a few people when this is actually different, but, the story is very parallel anyway. But I'm going to work under this assumption. And it turns out that in this case, in the balance range, the Archimedean root number is equal to minus 1, which means that the global root number is also minus 1, being the product of all those, okay? Which basically means that for all balanced triples kappa lambda mu, so for all kappa lambda mu whose weights satisfy these inequalities, the central critical L value is identically 0, it is just 0. So the center in this case turns out to be this number. It's the sum of the weights by 2 minus 1, okay? So the central critical value is 0, which means if you're hoping to construct some periodical function interpolating these, you can easily do that, it's just 0. So there's that part of the story. It's not interesting, and the arithmetic is governed by the Gross-Kudla conjecture in this case, which basically predicts that, like, the derivative of the L function of this triple product at this central critical point should be given in terms of the Bloch-Beilinson height of a diagonal cycle. Okay, so this is sort of the story. The picture in the balance region where the sign is minus. Now we're going to move to a neighboring region where G is dominant, meaning that you fail the triangle inequality in favor of G, okay? Somehow the weight of G is greater than or equal to the sum of the weights of F and H. So we're in this range. So basically what I'm depicting here is that I'm fixing the weight of F, and I'm basically, I mean, this is the weight of F, or this is the weight of F, and I'm basically plotting weight of G against weight of H. This is what this picture shows, okay? So in this case, the global root number turns out to be, it will also be plus 1, but the Archimedean root number turns out to be plus 1 in this range of specializations. As a result, like, the global root number in this range is plus 1. This is what this signifies. The global root number when you look at specializations within this range. So this superscript signifies that. So it is plus 1. And in this case, GGP governs the arithmetic. So the central critical L value should be given in terms of some sort of a period integral, like some trilinear form. And this is really, like, this was explicitly computed in, I guess, Ichino's and Milnon's work, Milnon's work. And so the L value is computed in terms of some certain period integrals, which one can explicitly compute. And based on this computation, one can prove that these vary well as kappa lambda mu vary. So these vary well. And as a result, like, that basically means that, like, one can construct a G-dominant periodical function interpolating the central critical L values or these L functions or their square roots as kappa lambda mu vary. So one can interpolate them. So you basically obtain a periodical function in what the so-called in this ring R3, which is the which is the complete tensor product of the the corresponding Hecke algebras. So we have this periodical function interpolating values only in this red region, and we can ask the same question again. Like, although, as I said, like, this set of points also in this picture, although it doesn't look like that, like the red, all the classical points in this red region are dense in the entire weight space. So you can really, like, approximate any point here by points in the red space, which means you can actually consider limits of these objects as you approach to blue points. Okay, so as these things calculate the L values in the red range, and then, like, if you basically approximate the blue points with those from the red range, what is the meaning of this? Okay, so this is basically what we're asking. So this is the question in the spirit of BDP is that if you see this is another dangerous use of delta. So if you restrict the G-dominant PDK function to the balance range, that's what it means. What arithmetic meaning can you hope? Okay, so is this something, does this have a arithmetic meaning? And again, the answer is given by Bertolini, Segoso-Menorecci, and Darmon-Roger, that this G-dominant PDK function can be recovered as the logarithm of a big diagonal cycle. Okay, and remember that these big diagonal cycles govern the arithmetic in the balance region, and this G-dominant PDK function lives here. So they somehow interact through this relation. Okay, so this is the second example of this wall crossing principle. And now I'd like to talk about applications of this to the Artin formalism for the G-dominant PDK function when you somehow identify the parameter spaces of G and G conjugate. Okay, so I'm basically insisting that specializations of G and G conjugate are just the same. So this is basically the locus where I'm considering, formally. So I'm looking at the hyperplane kappa lambda lambda in the 3-parameter weight space. So basically, lambda lambda corresponds to specializations of this. And there, if you restrict FGG conjugate to W2, you're going to have this factorization. So this is basically, if I think of this as a family of degree 8 motifs, this will factor as a family of degree 6 motifs and a degree 2 motif. Okay, that's what the picture is going to be. And we have Artin formalism for those, and we ask, is there a corresponding periodic Artin formalism? So how does the periodic function, when you take this G-dominant periodic function on W2, how should this factor to reflect this decomposition here? So that's the question we're asking. But the sad news is that this has no direct link to L values. So the usual Artin formalism has no bearing, because if so remember that this periodic function interpolates only the L values in the G-dominant range, whereas this hyperplane has no G-dominant points. You're asking lambda to dominate over kappa and lambda together, and that's not possible, okay? So you're asking the weight of lambda should be greater than or equal to weight of kappa plus weight of lambda, okay? Which, that basically means that, there are no such points, which means that, this hyperplane contains no G-dominant points, which means, there's no link to L values, so this might have a silly answer, no answer, whatever. But the key insight to attack this is that, well, although this is empty, if you look at balance points in this range, they are dense. Okay, you have lots of balance points. So we're going to again, cross the wall and apply, this results of Bertolini, Segoso-Menorecci, and Darmon-Roger. You basically restrict this to, if you look at the G-dominant periodic function on the hyperplane W2, but the balance points there. This is a periodic avatar for the central critical derivatives of L series in the balance range. Okay, so we have this dense set of data, which allows us to interpret these elements as the derivatives of L series in the balance range. Okay, so I'm basically just invoking this wall crossing principle for the triple product. Now, let me just assume that, this is a bit technical, but let me assume that the global root number for F is -1, as was the global root number in the balance range. Remember that this is basically how things work for us under our assumption on the local root numbers. This is -1, and I'm assuming that the root number of F is -1. There should be a parallel story when it is +1, okay? But that is probably much more complicated, okay? I can tell you later on, if there's time, but this is somehow, in some sense, it should be just for simplicity, but I cannot say anything reasonable in the supplementary case. That's why the assumption will have to be there, unfortunately. So the assumption that I'm going to work under is the global root number for F is -1, and in this case, you see, basically, if I'm looking at classical points, kappa lambda lambda in my hyperplane, which are balanced. So in that case, you see the degree 8 L function will vanish at the central critical point. So I'm interested in the derivative now because the L value vanishes. So the derivative of this degree 8 L function at the central critical point factors as the L value of the degree 6 thing times the derivative of the degree 2 thing. Okay? So again, just remembering that this G-dominant periodic function is a periodic avatar of those, this value is a periodic avatar of those, which means that it's a periodic avatar of those. So to probably to factor this correctly, we need to understand what the periodic avatar of those should be. Okay, so what is the periodic avatar of those? Well, here is, I mean, based on this heuristic, this is basically what you get. So, you know, the periodic avatar of like these degree 6 L values where the sign is plus is probably this periodic L function. Okay, you can interpolate this probably into a periodic L function. Whereas the periodic avatar, here I just basically put a periodic avatar of these central critical values, the derivatives at these central critical points. So that's what the factorization should look like. So you're factoring this degree 8 periodic L function, the G-dominant periodic L function. You get the balanced periodic L function here times whatever this means. I mean, this is something that you cannot state as a conjecture, but basically here is what turns out to be the correct way of stating this. So this factorization should read up to like completely actually explicit factors. This is given as the degree 6 periodic L function times logarithm of the big Beilinson-Kato class for the self-dual twist. So this is the conjecture. So this degree 8 periodic L function should factor as the degree 6 periodic L function times the big logarithm of a big Beilinson-Kato class. Now, why, again, this basically deserves a name to be called the periodic avatar of these derivatives. And the reason is actually, like, you know, it's essentially due to Perrin-Riou, which, like, you know, she proved this in a non-ordinary case, and one can extend it to the ordinary case. And the formula of Perrin-Riou reads as follows. If you take this big logarithm of the Beilinson-Kato class, the big Beilinson-Kato class, specializes to kappa, a specialization of this family F underlined, what you get is a linear combination of the derivatives of the two periodic L functions attached to the two different P refinements of your new form, okay? So, you know, F underlined kappa, I'm assuming that kappa is a crystalline specialization. So this will be a new form of level NF. And as such, it's going to have two P stabilizations. So its Hecke polynomial is going to have two roots, alpha and beta. And like, you know, attached to those, you're going to have P refinements, and you're going to have two periodic L functions. So derivatives of these two periodic L functions at the central critical point actually compute, it can be like put together to compute the logarithm of the Beilinson-Kato class. So this is indeed a periodic avatar for the derivatives, okay? So this is somehow justified, like, you know, I mean, you know, some, like, you know, this is somehow justified, like, you know, to put here. I mean, you can conjecture anything. So what evidence we have for this? So the first thing one can prove is that if this G underlined is a CM family, you can prove this conjecture in full, okay? But somehow this is cheating because in this case, there is like further factorization, which allows you to reduce this to like a comparing L values essentially, like or like a factorization problem that is interesting for a smaller degree motive, a family of motives basically. So this is somehow the cheat case, but it works. Like when G underlined has CM, this conjecture turns out to be true. And actually, well, we had also, like, you know, I guess with Ryotaro, we also proved, like, you know, an algebraic variant of this, which I'm going to say something in a different context later on. And we could actually, like, you know, conditionally prove this, conditional on the truth of the Gross-Kudla conjecture. I'll say a few words about this. So this conjecture also holds in full, so long as the Gross-Kudla conjecture holds for triple products of eigenforms of weight 2. So this is about complex L series, okay, in the balance range. And somehow, if this conjecture holds for eigenforms of weight 2, the result follows. And, like, you know, this is somehow the subject of the work in progress by Yifeng Liu, Xin Yuan, Shou Zheng, and Wei Zhang in progress. So I guess one serious complication, which I don't know if this is, like, you know, going to be treated in their work, is that I need a dense set of weight 2 points, like, you know, for this, like, you know, I need a dense set of weight 2 points that these families F underlined, G underlined, and G conjugate underlined specializes to, which means that I need to work with forms which are non-semi-stable at P. So that could be an issue, like, you know, for this. But I mean, when I last talked to Wei Zhang, this was, like, I guess, more than 2 years ago, he thought this is not possible, but I don't know, like, you know, if things change on that front. But then, like, you know, we're interested in this formula in a very degenerate case, like, you know, this, like, you know, the underlying, underlying automorphic representation, so to speak, like, you know, decompose into, like, you know, two automorphic representations on a smaller group, okay? So this factors. So in this case, Hangshui in his paper, I think from 2015, and I thank Daniel Desanier for pointing this out, he remarks that, like, the Gross-Kudla conjecture in this degenerate scenario should follow from the arithmetic GGP for the general case of the arithmetic GGP for U2 cross U3. I haven't checked the details, unfortunately. I'm waiting for like a good PhD student to do this probably for me. But yeah, Angshu has sounded positive that it should really work. But yeah, I mean, someone needs to check the details. But yeah, I mean, so basically we have this results based on, subject to this work in progress by these people. Now, let me just sketch the proof in this case, okay? So, so to speak, how do we connect all this to the arithmetic GGP? You see, some of this periodic function is constructed out of explicit GGP formula, and some of the proof of this factorization requires the arithmetic GGP formula in a different range, okay? So the first thing is that, remember, on the right-hand side, I have the log of the Buyukboduk class. I'm going to replace it with the log of the Heegner point squared. I can do this thanks to, a family version of Penrose conjecture, which, one can easily prove these days. I mean, easily meaning after the work of Bertrand Darmon and Venorici, it's actually, their proof essentially works to prove that this big Bayesian, the logarithm of the big Bayesian class is related to the square of the logarithm of the big Heegner cycle. So this is basically the right-hand side. And the left-hand side, thanks to the work of BSV and DR, Bertrand Venorici and Darmon Roger, you can recast this as a big logarithm of a diagonal cycle. Okay? So this is basically that. So this big logarithm is trivialized with respect to some differential, which I'm not going to specify. This is this omega f underline g underline g conjugate underline stands for that. All right. So here is basically the first step. So we want to prove this equality, and we want to prove this equality for the families. It suffices to prove this for special. It suffices to prove that this equality holds if you specialize this to a dense set of points. Okay, and the dense set of points that I'm going to choose to work with is going to be the weight 2 specializations. Okay, I'm going to insist that I work with weight 2 specializations of these families f underlined, g underlined, and h underlined. So basically, for such specializations f, g, g conjugate, which are weight 2, it suffices to prove that, if you specialize this to that point, this is equal to the right-hand side. Now, if you specialize this to f, g, g conjugate, okay, these are specializations of the family f underlined, g underlined, and g conjugate underlined. That's the notation for that. So this quantity here on the left-hand side, this logarithm, turns out to be the same as the Abel-Jacobi image of the diagonal cycle calculated against the same differential omega. Okay? So that's basically the left-hand side. Whereas the right-hand side, well, this is basically, this is a periodic function. It interpolates the corresponding degree 6 L value. There's a typo here. There should be an H0. There's a degree 6 L value normalized by, canonical choice of a period. So I'm going to call this script L. So this is the degree 6 L value times, again, the same, the Abel-Jacobi image of the Heegner point evaluated against omega f, the differential of f. So this is basically this is what the conjecture reduces to. Prove this equality holds for a dense set of specializations of weight 2. Now, what data we have is, well, okay, the Gross-Kudla conjecture tells us that, this height of the diagonal cycle computes the derivative of the degree 8L series, which factors as a degree 6L series times the derivative of the degree 2L series, which one can then compute using the Gross-Zagier formula as the Néron-Tate height of a Heegner point, or its extensions in this case. So then basically we have this relation between diagonal cycles and Heegner points. So by the way, yeah, so this basically tells you that we reduce to establishing a relationship between diagonal cycles and Heegner points. Okay, that's basically what this conjecture seems to require. And the first connection comes through the arithmetic GGP for these different groups basically. So this is the connection we have. But again, this still says nothing, right? I mean, we want to compare maybe diagonal cycle or the Abel-Jacobi image of this against the Abel-Jacobi image of the Heegner cycle. So how do I get from here to there? So you see, the point is that this diagonal cycle is it's a codimension 2 cycle on this threefold, the self product of the modular curve, threefold self product of the modular curve with itself or it's like an FGG conjugate part. And this is an object that we cannot put our hands on. Whereas the Hegnar cycle is a codimension 1 cycle on the modular curve, or its F part. And this actually object is relatively simple. Since I'm working with a wave 2 form, this is simply the Murday group of the underlying abelian variety. So these live in very different worlds. So a priori, there's no direct comparison, of course. Okay, but there's a remedy which, following Darmon-Roger-Sol's and Daub's thesis, there's a construction of a so-called Chow-Hegnar cycle, which actually, probably was well known well before that, but they call this object Chow-Hegnar cycle, ZFGG conjugate, which lives in the same space that the Hegnar point lives, and it has the following properties. So this object knows everything that you want to know about the diagonal cycle, and also it lives in the same space that the Hegnar point lives. So that's probably good news. So here are the properties. So the Bloch-Beilinson height of the diagonal cycle that you're interested in, remember, this is basically the object that you're trying to, this is the equality that you're trying to make use of. So this Bloch-Beilinson height can be computed in terms of the Néron-Tate height of the Chow-Hegnar point, okay? So that's basically that. So in place of this, you can place the Néron-Tate height. All these are inequalities up to simple factors. So you see, I'm not writing equality here. Just take this with a grain of salt. So now, likewise, if you just do the same on the Abel-Jacobi images, they also match up. So the Abel-Jacobi images of the diagonal cycles against this differential actually can be computed as the Abel-Jacobi image of the Chow-Hegnar point against differential omega f. So these two things also agree. Very good then. So basically we can just put everything together now. So I'm going to assume, so we're working with this specialization f, and I'm going to assume that so basically this is its self-dual twist. The derivative of so I'm basically assuming that the L value at the central critical the L function at the central critical point for this critical self-dual twist has order of vanishing no more than 1. In fact, exactly 1. That's what I'm assuming. And I can do this without loss of generality because if it fails, the required equality that I'm trying to prove, like this is that, one can check that this actually reduces to 0 equals 0. So if this holds, you can go through Howard's Fusat-Gross-Zagier formula and the Gross-Kudla conjecture, which we assume. You can prove that under this assumption, what you're trying to prove is just 0 equals 0. So I'm going to assume that the derivative of the twisted L value at the central critical point is non-zero. And in that case, Howard proves that this isotopic component of the Murday group, so this isotopic component is given by the square root of the Neben type. So this is wild anyway, so the square root is well defined. P is greater than 2, remember. So if you look at the P isotopic component, if you look at the isotopic component of the Murday group under this action, the rank of this is just 1, okay? Now, the thing is, both the Hegnar point, the peak Hegnar point, and the Chow-Hegnar point lives in this rank 1 module, which means they are related to one another by a scalar. So what this scalar should be will be read through this relation, basically. So the relation we have is that, so first of all, this is one of the steps. So in this step, we saw that the Abel-Jacobi image of the diagonal cycle, it can be recovered from the Chow-Hegnar point in this manner, okay? And so basically this is that step, and basically as I said, the Chow-Hegnar point is a multiple of the Hegnar point by something. Whatever that something should be, should also satisfy. It should also match with this or concur with this relationship, and that sort of tells you that constant should be the degree 6 L value. So ultimately, what you prove is that the Abel-Jacobi image of the diagonal cycle agrees with the Hegnar point up to this degree 6 L function, and that's exactly what you wanted to prove. Okay. So this is how the story goes, and how we rely on the work of BSV and Darmon-Roger to prove this factorization result. Of course, another key input would be the Gross-Kudla conjecture and the Gross-Zagier formula. So that's basically the rough argument. All right, so now you see, right now we've basically looked at sort of the like a periodic counterpart of the GGP for G spin 4 cross G spin 3. Like, this is split form of this would be GL2. This split form of this would be GL2 cross GL2 over GL1. So this is sort of what we looked at. I guess the next thing to consider, based on this silly observation, that maybe just look at G spin 5 cross G spin 4, and the split form of G spin 5 is simply GSP4. So that means we're now looking at forms on GSP4 cross GL2 cross GL2, and just see, like, if there is a parallel story. Hopefully not. It would be very boring. Yeah. So it's, I mean, just take my word for it. There's a new phenomenon in this case. In fact, like you see, the previous case we explained things by wall crossing. Now in this case, a new phenomenon occurs, it turns out, which you require double wall crossing, and probably you'll have to do this multiple times. So I'll try to explain what I mean by this. And I apologize in advance that from this part on, things are going to get very sketchy, because many things that I make conjectures about don't even exist in the first place at this time, okay? So it's built on farther vast conjectures anyway. So, but there is a picture, and there are some cases you can prove this. But yeah, so I'll get to that. So let's see. All right. So I start with an algebraic automorphic representation on GSP4 cross GL2 cross GL2. So pi is basically, pi corresponds to a holomorphic Ziegel form of weight K1, K2 on GSP4, with K1 is greater than equal to K2, and they're both at least 3. And sigma 1 and sigma 2 correspond to forms on GL2 cross GL2 with weights C1 and C2. So this is what the GGP, well, some of the GGP regions look like, okay? I mean, this is not going to make sense, but they are just given by some interlacing relations again. So this is 5 of the 9 GGP regions. I guess this is probably a bit more enlightening. So this is what the corresponding diagram looks like. You have 9 regions. So by the way, yeah, this picture is borrowed from the paper of Loeffler and Zerbes. Okay, so, and in fact, this is the picture. This is the reason I'm giving this slide talk is because of this picture. There's no way I could draw this. So basically here, what we're plotting is we're fixing K1 and K2, the weights of the Ziegel form pi, and C1 is on this, like C1, this is the C1 axis, and this is the C2 axis, okay? So for example, for the region A, the requirement is that C1 should be at least 1, so that determines the west border here, okay? And C2 minus C1, the difference of these, should be at least K1 plus K2 minus 2, so that determines the east border here, okay? So this is the line, C2 is equal to C1 plus K1 plus K2 minus 2, okay? So this is basically the region A. One thing probably that I should record here, if C2 and C1 is equal to 0, we're doomed. Okay, so this is the case of interest for us in the future. I'm going to identify, again, the 2 GL2 forms, which means I'm going to identify C2 and C1, and that will produce no points here. Okay, that's basically something to keep in mind. So again, like also, like I colored the stuff that I'm going to say, I colored the regions that I'm going to say something about, and here plus and minus blah, 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 basically just stand for the corresponding root numbers. Okay, so in the plus regions, we're going to have, these are definite GGP regions, we're going to have hopefully non-zero L values generically and a periodic L function. And the minus regions, we expect to have cycles and an arithmetic GGP, like, which sort of like calculates the derivative of the L function. So let me just talk about the definite GGP region. So that's going to probably clarify one of the things that I said, like, what does a toric period look like? I mean, this is like a generalization of this. So in this case, what we look at is, we have this group H, GL2 cross GL2, embedded into GSP4 in a somewhat standard way. And I'm going to put sigma underlined. This capital sigma underlined is going to be the product of 2 families, sigma underlined and sigma 2 underlined, 2 Hida families on the group H. So this sigma underlined is a family on H. So these are families on GL2 cross GL2. So then in this case, basically we can consider the GGP periods, like the periods basically attached to phi cross sigma lambda 1 lambda 2. So phi here is a vector in pi, and sigma lambda 1 lambda 2 is a specialization. It's basically a vector corresponding to the specialization of this Hida family on H at lambda 1 lambda 2. So basically what you do is you pull back phi to h and then multiply by sigma and integrate, okay? So this is the period integral. And for some suitably chosen phi and sigma, this should interpolate well as you vary lambda 1, lambda 2 in this family, okay? So that's basically the expectation. So this club suite, notates the region again. So there are 9 of them. And you see, there are very small amount of work. When this is the region C, this is work in progress by Andreatta, Bertolini, Seveso, and Menarucci. And when the region is F, that's another hypo. So basically, if you're here or here, there's some partial work in progress, okay? So otherwise, we don't know this object exists. It's entirely elusive. So in the remaining 4 regions, we don't know, how the construction, how this is going to work. And that's what I'm saying. I'm going to talk about the A region. So this is the first warning that everything I'm going to say is going to be based on the hope that this conjectural picture will work through at some point. Now, in the indefinite GGP regions, now we have, we expect to have cycles. Okay, so when the global root number is -1, we expect cycles and an arithmetic GGP formula. So these are the 3 of the regions, B, B prime, and E. Okay, so these are just neighboring regions to the definite regions. When you cross the wall, you basically change sign. And so these cycles are available when the region is E, and this is again sketched in the work of Loeffler and Zerbes, and otherwise again they're completely out of reach. Okay, so a lot of things I'm going to say again is based on the conjecture that it will make sense in other regions too. Now here is basically the first thing one can ask. So if you start with the D-dominant pedicle function, maybe I should show you the. Yeah, so this is determined by these relations. So in the D-dominant region, you basically take sigma 1 and sigma 2 to be the same, okay? So the underlying motive is going to factor, but then the relation you need to satisfy is this. C2 minus C1 is going to be 0. It should be greater than or equal to K1 minus K2 plus 2. So it should be greater than or equal to 2. So it will not hold. So in the D-dominant region, you will not have any interesting points for the factorization problem that you might be interested in, sorry. So this is then still the same, this is a question of the similar sort. If you take the pedicle function in D region and restrict it to the hyperplane where the weight, where the parameters for the sigma, the GL2 factors are identified, how does this factor? Okay? And the story is very similar to the triple product in this case, so I won't say anything more. So basically, you answer this, or at least hope to answer when all the available tools, all the tools are available that you would require for this, is that you cross the wall to E and you somehow proceed there. So I'll fast forward to the case that concerns the region A. Now, again, this is the setup. So we take our family, my GL2 family, sigma 1 and sigma 2, are going to be chosen to be identical as sigma underlined. So in that case, basically this product, pi cross sigma underlined, is going to factor as a family of, so this is a family, you can think of this as a family of degree 16 motifs, 4 times 2 times 2, degree 16 motifs, decomposing into a family of degree 12 motifs and a degree 4 motif. Okay? So basically, the question is, if you take the pedicle function in the A region, you can ask, if you basically look at the points where these two things agree, when these two forms are taken to be the same, what factorization do we have of this pedicle function to reflect this decomposition? So now, again, the crucial point in the region A, that's what I said. You see, when you take these two families the same and the specialization is the same, the weights, yeah.
Going to this way, there could be some other ways, right?
Well, this is a preferred choice for now. That's a good question. The best way I can justify this maybe is through the algebraic analog of this. Maybe I can tell you, but maybe it's not convincing enough also. I convinced myself that this is the best way, but it could be easily wrong.
Sure.
That's actually the correct way of thinking. But I mean, what is the distance? That's a good question. Maybe I'll say something at the end. Yeah. Let me just see if I have time to say this. I'll get back to it if I have time. So if you basically insist that these two have the same specializations, in particular their weights are the same, which means the difference of the weights is 0. So and in the region A, you want to satisfy this inequality, which you will never satisfy. Which means, if you want to factor this, just looking at the L values, you won't be able to do that. Okay, there are just no L values that basically are relevant to this region if you're considering this factorization problem. Then, as previously, you jump regions. You move to B, okay? So in this case, when you jump regions, so the condition that you need to satisfy is again that C2 minus C1, which is 0, should be at least K1 minus K2 plus 2, which is at least 2. So unfortunately, if you jump to regions 1, you won't get anything either. So again, there are no arithmetically interesting points here that will somehow allow you to treat the points of interest as far as the Artin formalism is concerned. Okay? So which means we just jump again. And okay, why do we jump this way but not this way? That's actually a valid question. Maybe, but again, if you jump this way, as I said, that there's a problem, right? There are no points of interest also in the region. That was the original problem. So you might again have to jump to E again. So, okay, maybe that will also give something. I need to think about it, but you would need to jump again, anyway. But the main point is that, you need to jump again. I'll jump to C, all right? So this is basically the main reason. I just put this on the slide. So let's stare at this for a second again. This periodic health function in the A region restricted to the B region, but to the points where C1 is equal to C2, because these are the points that are relevant to the Artin formalism. This makes no sense. This set is empty. Okay? So we jump again. Now, what happens? So in the C region, the global sign is +1 for this degree, for these degree 16 motifs. And I'm assuming, again, you can assume the supplement of this too. I'm assuming that the global sign for the form on GSP4 is -1. Okay? But that basically means that the degree 12 motif, the family of degree 12 motifs will have also sign -1 in the C region. So here, the sign decomposition is going to be that plus is equal to minus times minus, which means this degree 16 motif is going to vanish to at least order 2 at the central critical point. Okay? So again, the heuristic in this case would be that this should be a periodic avatar. So basically, if you take the A periodic health function, restrict to the region C, which you basically get after jumping twice, and if you look at the points that of interest, C1 is equal to C2, this should be a periodic avatar for the second order derivatives here, which of course factors like this. So it should be a periodic avatar for those, which led us to conjecture that this A periodic health function should factor as the logarithm of some degree 12 cycle. We don't know what it is. Okay, so there's no constant. This is basically a conjectural object too, times the logarithm of the lemma Flach class. Okay, so this is the replacement for the Bayes-Cotte element. All right, so this is a conjecture that we formulated with Ryota Sakamoto and Oscar Rivero. Again, so what evidence do we have? I guess the only convincing evidence we have is that the algebraic counterpart of this holds, which basically concern what we call the module of leading terms. Okay. If you're working with in the Panchishkin situation, or numerically Panchishkin situation, this will be simply the generator of the characteristic ideal. But in this case, the problem is that, if you look at the local conditions determined, it corresponds to this region, they don't propagate well. Okay, they don't propagate to Panchishkin conditions. So basically, you need to come up with a notion of you need to come up with a correct notion of this module of leading terms. But in any case, somehow module of leading terms factor in this manner. So logarithm of module of leading terms for this family of degree 12 motifs times logarithm of this family of degree 4 motifs. Okay, and in fact, if the main conjectures, for example, for this pi holds, these two things would agree. Okay, so this would be the point. So again, as I said, these are some submodules of the Greenberg-Selmer group, basically, which you can define, and some of these control exactly the leading terms. That's basically what it is. So these really see the derivatives. That's basically the main point. And a further, potential evidence in progress, though, is that this conjecture holds if pi is a usually left. If you cheat and look at this degenerate case where you can factor this pi, this should work out. This is work in progress. It's still very technical, so we didn't have time to finish this off. But this seems to be correct. So maybe I'll quickly say, why I like this better. So basically, at least in the algebraic side, we have for each of these regions. So this is a region. This is a GGP, one of the GGP regions. We have a corresponding choice of a Greenberg submodule. So let's say, so T is this degree 16 motif or family of those. So this is basically a family of those. So we have this is like the Greenberg. This is a Greenberg submodule. So this has rank 8 sitting inside here. Okay. Now, for example, given two of those, so if X and Y are two of those regions, you can define the distance from X to Y as in the obvious way, right? I mean, if you take the Greenberg submodule for X, and then you just basically see, so the rank of this, F plus XT intersected F plus YT, okay? So in this case, it turns out that, for example, the A to B is 1, and then the B to C is 1, and then the A to E, which one is this? Sorry, I already, the A to C, sorry, yeah, the A to C is 2. Now, if you do this if you jump to D, nothing, you're not going to get anything again, as I said, right? Let me just show you the picture. Yeah, this is too small. Yeah, if you jump here, as I said, there's no points of interest when C1 is equal to C2, so you'll have to jump again. So just increasing your distance. So, and as far as the algebraic story goes, that means bad news. I'm guessing it means bad news also otherwise too. Yeah, I think so. At least if you believe in this heuristic, which I would trust, main conjectures would reflect this anyway. That I know what the story should be. I did in general. Yeah. Yeah. All right. Very good. I think. Whoa. I'm actually done. Yeah. So I'll take questions. Yeah. That's all I have to say. I went very fast. Sorry.
Well, great. We are a little tired. So,
well, that was my weekend. Yeah.
Any question or comments?
This one.
Yes. Will it give a higher rank Euler system kind of thing?
No, I mean, here it's not about the higher rank Euler system. You see, this is about the second order derivatives rather. So it's going to give you it predicts some regulator again, but it's not related to a rank 2 Euler system. Okay, it's really just like a mixture of this cycle here and the cycle here. Okay, so you're basically factoring the corresponding Selmer group, which is expected to have rank 2, and somehow you're factoring its regulator as the regulator of those two. Yeah, I don't think central critical. I mean, in this scenario, when you're looking at self-dual stuff, I don't expect higher rank Euler systems. Yeah, I mean, in families, that's what I mean. Point-wise, yes, maybe, but not in families.
Any other question?
Oh, you mean if you go there? I mean, I didn't think about it, but yes, I think from going from right to left is probably, yeah, it's probably a very parallel story. Yeah. I didn't think carefully though. Take it with a grain of salt.
Yeah, but with some sort of functional equation.
Probably, right? Yeah. Most probably they're probably indeed like this is probably the axis of symmetry indeed. Like, if we probably do everything here, probably it just follows from the functional equation.
yeah.
But again, no periodical functions at this moment, nothing. So no functional equations in particular, but yeah, but this is the general philosophy, I think. Thank you.
Any other question?
Essentially, it boils down to that. Yeah. Yes. It is exactly the same. Yes. Yeah, these are just like, given in terms of this GGP parameters indeed. And yeah, so exactly that. I mean,
Okay.
maybe this gives you a hint. I mean, maybe it doesn't. Let me just still show. Yeah, yeah, exactly. Yeah, so.
So any other question? Okay, so let's thank speaker again. We reconvene 12:15. Just on time.
Good. It's good that I finished early then. Sorry, I went too fast maybe.